Welcome back to Anatomy and Physiology 1 Laboratory. My name is Kevin Tokoph, and in this video we're going to discuss Exercise 7, which is the first half of the study of skeletal muscles. Alright, so first of all, before we go any further, skeletal muscles are the types of muscles that attach to the skeleton or to the bones, and when they contract, they pull on these bones and that generates movement. The other types of muscles generally we're going to look at in A&P2, and that includes cardiac muscle and smooth muscle. Obviously, we won't discuss those here. So as I said, skeletal muscles, they pull on bones to move the skeleton. As we've mentioned all the way back from Exercise 2 for organ systems, the skeletal system provides attachments for the muscles of the body, and then the skeletal muscles pull on these bones to move the skeleton, which generates movement. However, this linkage between the muscles and the skeleton is indirect. And it's indirect because rather than directly attaching to the bone, the muscles actually produce movement through a tendon. So for example, we're going to actually for this entire slide use the gastrocnemius or calf muscle as an example. But notice here's our calf muscle, the gastrocnemius. Notice, which it's in red, it does not directly connect to the calcaneus from the previous lesson, which was the heel bone. The connection is indirect because, as you can see here, we have this white tendon, which is actually called the Achilles tendon or the calcaneal tendon. So the connection between the calf muscle and the heel bone is indirect, and this is going to be the case with pretty much every muscle that we're going to see. All right. So now that we understand that the connection between the muscle and the bone is generally indirect via a tendon, let's go into some important terms that describe the function and structure of skeletal muscle. Alright, so first we're going to have an origin and insertion. These are really going to be the topic of the second half of this lab, which we'll cover on Thursday this week. Today we're actually going to be covering the actual anatomy, but origin and insertion have to do with the tendons on either side of the muscle. Alright, so the origin is the point of attachment toward which the force is directed. So what does that mean? Well, think about this. You possibly know how to contract your gastrocnemius. If you're standing upright on the floor and you go up onto your tippy toes, right? Maybe you've been in the gym and done calf raises. What's happening when you go on your tippy toes? Well, your toes remain planted on the ground, but your heel moves off of the ground. So the heel's going to move off of the ground. So what's happening is the force is being directed upwards. In other words, the gastrocnemius is pulling your heel upwards off the ground. So the origin is the point of attachment toward which the force is directed. So the origin would have to be up here on the top, at least of this picture. Okay? In fact, the origin of the gastrocnemius is, or are, the medial and lateral condyles of the femur. Remember, this is the distal leg. Femur is up here in the proximal part. So the origin is all the way up here in the medial and lateral condyles of the femur. For now, this is just an example. And it's the origin because the force is directing the heel upwards toward that. All right? That's always what the origin is. A second term is the insertion. The insertion is the point of attachment which is pulled towards the origin. Well, if the origin is the medial and lateral condyles of the femur, then the insertion would have to be the calcaneus, which is the heel bone. And remember, it's the point of attachment which is pulled towards the origin. So, because the calcaneus is pulled upwards towards the medial and lateral condyles, towards the origin, the calcaneus is going to be the insertion. The action of a skeletal muscle is just the movement that it facilitates. So for example, we've mentioned the calf muscle or gastrocnemius facilitates you going up on your tippy toes. Now the specific name of that movement is plantar flexion. So we would say that the gastrocnemius's action is plantar flexion. In fact, what we could also say, and I probably should have put this sentence up here by action, is since the gastrocnemius facilitates plantar flexion, we would say the gastrocnemius is the agonist of plantar flexion, or it's an agonist. There might be more than one muscle that does that. So if you have a muscle whose action is plantar flexion, then that muscle is the agonist of plantar flexion. We could also say that, in another example, if we have a muscle that promotes elbow flexion, then that muscle would be the agonist of elbow flexion. The agonist is the muscle that facilitates that particular action or movement. All right? Now, The antagonist is always the muscle that facilitates the opposite movements. So think about what plantar flexion really is. In fact, if you're actually sitting down, you don't even have to be sitting up. Plantar flexion would be, if you're laying in your bed, basically just sitting down, and you got your feet pointed upwards into the air. Plantar flexion, which is what the gastrocnemius does, would be to point your toes away from your head. And in fact, if you think about it when you're standing up, when you go on your tippy toes, that's true. Your toes point further away from your head. So the opposite movement would be to point your toes upward toward your head. And that movement is actually called dorsiflexion, which I have here. And there's a muscle that facilitates dorsiflexion. That muscle is actually the tibialis anterior. So because the tibialis anterior facilitates the opposite movement as the gastrocnemius, we would say that the tibialis anterior is the antagonist of the gastrocnemius. And the opposite would also be true. We could say that the gastrocnemius would be the antagonist of the tibialis anterior. Again, for now, this is just an example. All right? And one more term is the synergist. A synergist is just a muscle that facilitates the same movement as another muscle. All right. So we've really been talking about the gastrocnemius here, but we also have another muscle that's behind the it's deeper muscle behind the Achilles tendon. It's actually the soleus. All right. And since the soleus also facilitates plantar flexion, we have two muscles that do the same thing, we would say that the soleus is a synergist of the gastrocnemius. Or another way we could say that is the gastrocnemius and soleus are synergistic to one another because they're performing the same action. Okay? Another example of two muscles that perform the same action would be the biceps, which we'll actually go on to say today in class. The correct name is biceps brachii, but the biceps brachii and the brachioradialis, another muscle in the arm, they both perform elbow flexion, so we would say they are synergistic with each other. All right. Another example of antagonists would be the biceps and the triceps, which if you have any knowledge of the gym and resistance training, you know that the biceps promote elbow flexion, whereas the triceps promote elbow extension, two opposite motions. Therefore, those two muscles would be antagonists to one another. So hopefully this made sense. Let's now look at some structural classifications of muscles. So first of all, we have parallel versus pinnate muscles. So a parallel muscle is one in which the fibers, and you should be able to see the individual fibers, they all run parallel to one another. They all run in exactly the same direction. So here's one example of a longer muscle called the sartorius. This is actually what we'll see as the seatbelt muscle of the leg. But all the muscle fibers run in the same direction, and so this is a parallel muscle. All right, and it has parallel muscle fibers. The same thing's true of the rectus abdominis. Each one of these sections of the rectus abdominis, all of these muscle fibers run up and down parallel to one another. All right. Now, how does that differ from pinnate muscle fibers? Pinnate muscle fibers have a tendon, like here shown in the rectus femoris, right here. But all of the muscle fibers, instead of running parallel to one another, they actually run obliquely from the tendon. Okay, so for example, if we look at the rectus femoris here, we see that these muscle fibers run diagonally from the left side of this tendon, but then they also run diagonally in the opposite direction from the right side of it. And because these muscle fibers run obliquely from that tendon, we would say that these three muscles would be pinnate muscles and would have pinnate muscle fibers. And again, examples here that we'll look at would be the rectus femoris and the deltoid. In this class, we won't look at the flexor pollicis longus. All right? Another way to classify muscles would be fusiform, convergent, and circular. This has more to do with the shape of the overall muscle rather than the orientation of the muscle fibers. So the first type is a fusiform muscle. A fusiform muscle is one in which, notice we have a tendon on either side of the muscle, tendon up here, tendon on the bottom. And really what happens with a fusiform muscle is by the tendon, the muscle is thinner, but then it kind of bulges outward, and then it returns back inward. So it's thin but near the tendons, but kind of bulges out, but then returns to its tendon size towards the tendon. I guess that's the best way you could say it. Okay. Another way is the muscle fibers that exist between the tendons have approximately the equal size. So it can bulge out, but then it goes back in. An example of this, which we won't specifically look at in this course, would be the brachioradialis, which actually, as I mentioned earlier, was synergistic with the biceps. All right. Now here's a second one, a convergent muscle. Okay, a convergent muscle is one in which this Over here you can see is kind of whitish. All of this is going to be sort of a tendon. This might actually be an aponeurosis. I'm not sure off the top of my head. But the point is, all of this over here where it's white is a point of attachment. And notice it's a pretty large area for point of attachment to a bone. But notice how it starts off large over here, but as we run to the right, it tapers off and becomes very thin to a small tendon over here on the right side. We would say that the muscle fibers start over here at a very wide or large area of attachment, but then converge to a very small tendon. Therefore, we call this muscle, like the pectoralis major, the chest muscle, a convergent muscle. All right? And the last type, a circular muscle, sort of speaks for itself. I don't have a definition over here. It's pretty much circular. And usually these muscles are going to surround and control openings or orifices or sphincters of some sort. The two most notable examples that we'll see in this course are going to be the orbicularis oris, which control opening and closing of the mouth, and then also the orbicularis oculi, which do the same for both eyes. All right? So make sure you understand this, classifying muscles based on the orientation of their fibers, but also down here on their shape overall. All right? Now, let's look at major joint movements of the body. This is going to be very important. And when you name a joint movement, there's something you absolutely have to do. You have to specify the movement, but also the specific joint involved. So, for example, if we're talking about elbow flexion, so you flex your arms, which means decreasing the angle of your elbow joint. We already mentioned briefly that that action was facilitated by the biceps brachii. And so if we wanted to be very specific, we would need to say the bicep brachii facilitates flexion of the elbow. So flexion names the movement and elbow names the joint. All right, so we would need to specify both of those things. All right, let's actually start on the second row because these are actually a little bit more intuitive. So first of all, we have flexion. So flexion and extension go together. Those are opposite movements. Flexion and extension, you should understand the definition of those. Flexion and extension are always movements of the joint, but they occur in the sagittal plane. Okay, they occur in the sagittal plane. So in other words, if you were to sort of cover your arm in imaginary paint and do that motion, the plane that you trace out with the paint would be the plane that it moves in. So flexion and extension you could see occur in the sagittal plane. All right, but I need to specify what joint is moving. So flexion is a decrease in the angle of a joint. Okay, and this would specifically be shoulder flexion, because what I'm doing is I'm flexing the shoulder joint, moving my arm upwards as shown here in the sagittal plane. So flexion is always a decrease in the angle of the joint. Extension is always an increase in the angle of the joint, but it occurs also in the sagittal plane. This is actually shoulder extension. So if he starts with his arm up here, he'd be moving it downwards and then potentially behind his body. That would be extension of the shoulder joint, an increase in the angle of that joint, but in the sagittal plane. But these occur for the shoulder. Here's two more shoulder movements, abduction and adduction. These are very commonly confused, so make sure you understand what they are. Abduction means you're always moving the limb basically away from the midline or away from your body. So notice with abduction and adduction, these are actually occurring in the frontal or coronal plane. Still for the shoulder joint, but notice he's moving his arms away from his midline, right? So this would be like the upward phase of a jumping jack, moving his arms away from his midline upwards, but it's occurring in the frontal plane. Adduction is the opposite. It would be moving his arm back towards the midline, or we could say the downward phase of the jumping jack, but still for the shoulder joint, so this would be shoulder adduction, moving his arm or facilitating the shoulder joint so his arm comes back toward the midline. All right? We can make the same argument with the leg with abduction and adduction. Here in the hip adduction, this is abduction of the hip with a B. Abduction would be moving his leg away from his midline, as you can see right here. All right? Again, this would also be involved in the upward phase of a jumping jack. But you see here that with the hip joint, he's moving his leg away from the midline. So this would be hip abduction. And in the second case over here, he'd be moving his leg back toward the midline. So this would be hip adduction with a D. All right? And here we have hip flexion and extension. So for hip flexion, again, he is decreasing the angle of the hip joint in the sagittal plane. That means he's bringing his leg upwards like this. Okay, so this is hip flexion. And extension is the opposite. He would bring his leg backwards, and then could even bring it behind his body. And that is an increase in the angle of the hip joint in the sagittal plane, so this would be hip extension. All right? Here we have flexion and extension of the knee. Notice here it's the knee that's actually bending. Okay? So, knee flexion would be a decrease in the angle of the joint in the sagittal plane. Notice here that he's decreasing the angle of his knee joint, so this would be knee flexion. But here he's increasing the angle of that knee joint, and so this would be knee extension, increasing the angle of the joint in the sagittal plane. All right? And we'll go over pretty much most of these in class, but the main thing to understand about naming these major joint movements is you need to specify both the movement itself and then also the joint that's moving. For example, if I wanted you to say, what is the action of, let's say, the hamstrings? The hamstrings, those muscles are actually what facilitate knee flexion down here. If I said, what movement does the hamstring facilitate? Or in other words, the hamstring is the agonist of what type of movement? It would be only partially correct, so really incorrect, to just say flexion. Flexion of what? It's flexion of the knee. The same thing would be true of shoulder abduction. The muscle that facilitates that is your deltoid, a shoulder muscle. So if you said, what does the deltoid facilitate, it would be incorrect to just say abduction. Abduction of what? Is it the shoulder or is it the hip? So you would have to say for full credit, if I ask you what movement does the deltoid facilitate, it would be abduction of the shoulder joint, really. Okay, so hopefully this makes sense. We'll go over this in more detail in class. Now, we've got two more topics to discuss in this section. And the first question I want to ask is, how does muscle force, which we'll eventually call tension, you can see it here on this graph, how does muscle force or tension vary with stimulation frequency? So when you come to class, we're actually going to have a little machine. You can hook electrodes up, surface electrodes on your skin, and the machine applies an electrical stimulation, and if it's strong enough, you'll actually feel your muscle contract without even voluntarily contracting it. The machine actually, by applying electricity, stimulates your muscle to contract. And in lecture, you'll actually eventually talk about, when you do muscle physiology, that muscles are ultimately controlled through electrical signals, which is why that works. So the question is, what happens when we increase the frequency at which we apply that electrical stimulation? Okay? And frequency just basically means how much per unit time. So a low frequency would be like maybe 5 times a minute. High frequency might be like 1,000 times a minute. So just so you understand that. And here's a graph. Okay, so these arrows, these red arrows, indicate when we apply the electrical stimulus, and however high this curve gets on the graph indicates how much force was produced, or how much tension in this case was produced. So let's say we apply one electrical stimulation. We would get, if we graphed this graph of tension, we would just get something that looks like this. So right here at the peak, that was my maximum tension that was developed in the muscle when I applied a single electrical stimulation. All right? Now, as you'll talk about in lecture, what has to happen for muscles is, whenever there's an electrical stimulation, generally the muscle contracts, but then it actually has to relax first. Okay? And then, once it's relaxed, if you apply another electrical stimulus, it would do exactly the same thing. You'd see a second one of those. And a single contraction, a small contraction of that muscle, is termed a muscle twitch. So that's number one here. A muscle twitch is just simply a small contraction of the muscle. Doesn't have to be big at all. But what happens if, let's say we apply an electrical stimulus, but before the muscle ends up relaxing, before it finishes its relaxation, we apply another stimulus. So it hasn't had a chance to relax, we apply another one, and maybe another one. Well, we get what's called wave summation. All right, so let's read this. If we electrically stimulate a muscle a second time before the first contraction is complete, or in other words, before the muscle has relaxed, the second contraction will yield more tension, or force as we call it, than the first contraction. So here's our first arrow. We apply an electrical stimulus so we get some tension. But notice here, the muscle has not completely relaxed, because if it did, this curve would go all the way back down to 0. It hasn't completely relaxed at this point, but notice we apply a second electrical stimulus. And so what happens is we get more force. And then it starts to relax a little bit more, but it doesn't relax all the way. And we apply a third stimulus, and the force goes even higher. So what's happening is wave summation. So whenever we apply another electrical stimulus prior to the muscle finishing its relaxation period, the next force development will actually be greater. There will be more tension developed in the muscle. All right? This is called wave summation. All right? And it's a very general term, because what we can do is, as you see over here, we can actually start doing more and more and more electrical stimuli in rapid succession. And so we can get what's called tetanus. So for example, if we begin electrically stimulating the muscle with very high frequency stimuli, as in electric stimuli, the tension produced will increase more and more and more and more up to a point. All right. So the first type of tetanus we have is called unfused tetanus. Let's look at the graph. So notice, instead of having just 3 relatively separated electrical stimuli, I now have some that are much closer together. So first electrical stimulus goes up in tension, then goes back down a little bit, but doesn't relax all the way. Then I keep applying electrical stimuli, and notice the tension developed gets higher and higher and higher. And it could actually increase. It could keep getting higher and higher and higher up to a certain point, which would be the maximum, but it can keep getting higher and higher and higher. And if you graph this, and you can actually distinguish each individual contraction from the next, so notice here, you can distinguish each individual one. There's actually 5 total. And that's what we call unfused or incomplete tetanus. And the key with that, for it to be unfused or incomplete, is you would have to be able to distinguish each individual contraction. But if we now crank up the frequency even more, as you can see here by these very tightly packed red arrows, you can get what's called fused or complete tetanus. And this is when the individual contractions are completely indistinguishable from one another. So when you have fused tetanus, what you'll see is just, it'll go up, but then it'll just pretty much be just a line. There's absolutely no relaxation, really. It just keeps stimulating and stimulating, but you can actually see, if you look really carefully, this line actually has a positive slope, so it's actually increasing. Okay, but that's fused tetanus. So tetanus in general is when you start cranking up the frequency to really high frequency electrical stimulation of the muscle, and then you just get more and more and more tension up to a certain point. All right, the difference between these two tetanus types would be whether or not the individual contractions are distinguishable from one another, okay? And the mechanism by which wave summation and tetanus occur, you'll actually discuss in lecture, and it actually has to do with calcium that's released from the sarcoplasmic reticulum. We will not talk about that in the lab. The second question we have is, how does muscle force vary with the stimulation intensity? So we just looked at frequency, but what about the intensity? All right, well, here I have another graph, and you see here red lines on the bottom that are present always, and then blue lines that kind of extend upward, up to a certain point, and so on and so forth. All right, so in this case, we're not varying the frequency of the electrical stimulation. We're actually varying how strong it is, its intensity. And in general, when we're talking about the intensity of electrical stimuli, we're talking about voltage. And we know high voltage, you see these signs on all sorts of power line areas. Means don't touch. The electricity is very strong. It'll kill you if you touch, potentially. So we're measuring voltage for intensity. All right. So what happens if we stimulate with very low intensity, very low intensity? We don't get any contraction. The muscle doesn't contract at all, okay? This 0 line right here, we basically have to hit this 0 line in order to get any contraction. This 0 line in this case is what we call the threshold. Okay, you'll talk about this in lecture. It's more or less the threshold of excitation. But in this case, we're just going to call it the threshold. These first 2 stimulations of 1 and 2 volts, in this case, would be sub-threshold. It's subthreshold because they're so low voltages, the intensity is low enough to the point where they don't even elicit a muscle contraction, as noticed by the force of contraction is 0. There's no contraction at all. Okay? So these two stimuli, 1 and 2 volts, would be subthreshold stimuli. All right? But notice when I get to 3 volts, that's apparently enough to hit the threshold. And so I get a little contraction as noted by this 1 here, and everything above threshold is in blue. Okay? So this 3 volts apparently was enough intensity to actually elicit a muscle contraction. It wasn't much, it was just 1, whatever these units are, but again, it produced some force. So this is what we call a threshold stimulus because 3 volts actually did elicit a contraction of the muscle, so we did hit threshold. All right, so if we go from 3 basically up to 6, these are threshold stimuli because they elicited a muscle contraction. In fact, once voltage is applied above the threshold, increasing stimulation intensity increases the force of contraction up to a point. So you see between 3 volts and 6 volts we have the force of contraction increasing, which makes sense because the voltage is increasing, or the stimulation intensity is increasing. Now when we get to 7 volts, it's still increased from 6, so it's higher than it was at 6 volts, but notice after 7, it doesn't go any higher. So between 7 and 12 volts, we've apparently hit the maximum force of contraction given the stimulation intensity. That means that these 7 through 12 volts, these stimuli in the last half of this graph, these are called maximal stimuli. And that's because the maximum force generated is elicited by a maximal stimulus. Because apparently at 7 volts, even if you increase the voltage higher than that, the force of contraction won't increase anymore. Okay? So that's the maximum force that that muscle can generate. All right? So let's actually review these last 2 questions. How does muscle force vary with stimulation frequency? Well, the answer to that question is, as you stimulate the muscle electrically with higher frequency, so more and more and more per unit time, the force that develops increases. Second question, how does muscle force vary with stimulation intensity? Well, below the threshold you don't get anything, but assuming you hit the threshold, as you increase the stimulation intensity or the voltage, you get more force. More tension develops in the muscle, up to a point, which is the maximum stimulus. But the point is, as you increase stimulation intensity, the force developed does increase, up to a point. All right? So, again, we'll look at the anatomy of the muscles in class. That'll be up to you to learn, although we will go over some of them in person. But hopefully all of this material made sense. So we've got some of the physiological and anatomical features of muscles. We went over a little bit of major joint movements and so forth. And then make sure you understand these 2 questions and how they apply to muscles. All right, thank you for watching this video, and I will see you in class. And then the next day we will do the second half of muscles, which involves origins, insertions, actions, and movements. Thank you.